Set a pendulum swinging in a room and leave it. Come back an hour later, and it has slowed. Come back the next day, and it has stopped. The bob hangs perfectly vertical, perfectly still, and everything that was once motion has bled away into the air, and the pivot, and the slow, indifferent warmth of the room. This is so ordinary it barely registers as a physical fact. It feels more like common sense. Energy leaves, motion stops. Given enough time and enough loss, everything settles. Carry that intuition downward, not just pendulums, but everything. A vibrating string loses its vibration. A spinning top loses its spin. Cool something down far enough and the thermal motion of its atoms slows, the jostling and colliding that we call heat gradually quieting as temperature drops. Cool it further, and it quiets further. The logic seems to have only one destination. Strip away enough energy, and what remains is a system that has finally, completely stopped. That destination has a name in physics: the ground state, the lowest energy configuration a system can occupy. And for most of history, the assumption was never seriously questioned. The ground state meant stillness, zero motion, zero energy, the bottom of the bottom. Something refuses that conclusion, not because a measurement came back wrong, not because an experiment produced an unexpected result, but because of what the universe turns out to allow and what it does not. The moment you try to construct a state where a particle sits motionless at a fixed location, the framework pushes back, structurally. So, what is the rule being violated, and where does it come from? If you like exploring questions like these, feel free to leave a like and subscribe. And if there's something about the universe you find yourself wondering about now and then, drop it in the comments. It might become the next question we dig into. For now, let's get back to that question. Understanding why requires starting not with energy but with something more basic, with what it actually costs, physically, to know where something is. Stillness sounds simple. An object that is not moving is just sitting there, occupying a location, doing nothing. But stillness is actually a very specific physical claim. It says two things simultaneously. It says the object is somewhere in particular, a fixed position, and it says the object has no momentum, no tendency to move in any direction at any speed, both at once, completely and precisely. For a pendulum that is fine, for a grain of dust that is fine. At the scales where classical physics operates, there is no tension between knowing where something is and knowing that it is not moving. You can have both. The universe at that scale offers both without complaint, and nothing about the physics of large objects suggests the combination should ever be problematic. A rock sitting on a table is somewhere specific, and it is not moving. That is the whole description. Nothing is left out. Shrink the object down, not to dust, not to a cell, not to a molecule, down to the scale where quantum mechanics is not a correction or a refinement, but the only accurate description of what is happening. At that scale, the claim that something has a precise position and precisely zero momentum stops being a description of a very still object. It becomes a description of something the universe does not contain. This is not a statement about difficulty, not about the clumsiness of instruments or the limits of what can be measured. That framing, which is how the uncertainty principle is often introduced, makes it sound like a practical inconvenience rather than a structural fact. The issue is not that measuring position disturbs momentum, though that is also true. Position and momentum are not two independent properties that happen to be hard to pin down together. They are structurally coupled at a fundamental level. The precision available to one is paid for directly by the spread forced onto the other. Not approximately, not on average, exactly, and always. Nail down the position completely and the momentum becomes entirely undetermined, spread across all possible values with no preferred direction, and no preferred magnitude. Allow the momentum to approach zero with increasing precision, and the position responds by spreading across space without bound, the particle becoming less and less locatable the more its momentum is constrained. The two properties trade off against each other in a relationship that has a precise mathematical form and no exceptions. Stillness, defined as precise position and precisely zero momentum at the same time, is not a state that is difficult to reach at quantum scales. It is a state that does not exist there. There is a version of the uncertainty principle that almost everyone encounters first, and it is subtly wrong in a way that matters here. The version goes like this. When you measure a quantum particle, you disturb it, and that disturbance is what creates the uncertainty. The act of looking changes what is there. If only we could measure more gently, more carefully with better instruments, we could in principle recover both properties cleanly. The uncertainty is in the measurement, not in the particle. That framing makes the principle sound like a practical limitation, a consequence of the fact that probing something small inevitably jostles it, and there is a grain of truth in it at a surface level. Measuring a particle's position does involve an interaction that affects its momentum, but that interaction is not the source of the uncertainty. It is a symptom of something that was already true before any measurement took place. The uncertainty is not introduced by observation. It is a feature of what quantum states actually are before anyone looks at anything. A quantum particle does not have a precise position that gets blurred when you measure it. It exists in a state where position is genuinely spread across a range of values, each with its own probability, and that spread is physically real. The particle is not secretly at one location while appearing spread out due to measurement limitations. The spread is the reality. Similarly, the momentum is not a hidden precise value waiting to be uncovered. It is itself a distribution, and the width of that distribution is not independent of the width of the position distribution. They are connected by a relationship that holds regardless of whether any measurement is happening at all. This matters enormously for what comes next, because if the uncertainty were just a measurement problem, you could in principle imagine a particle sitting still at a fixed location, even if you could never confirm it experimentally. The stillness would be real even if unverifiable. But if the uncertainty is structural, if position spread and momentum spread are features of the quantum state itself, rather than artifacts of observation, then a particle with a precisely fixed position and precisely zero momentum is not just unverifiable. It is not a possible state for a quantum system to occupy. The universe does not have a version of that configuration on offer, and no refinement of measurement technique changes that. Take everything established so far and apply it to a specific situation. A particle trapped inside a small region of space, not metaphorically trapped, but physically constrained by a potential well, a region where the energy landscape rises steeply at the boundaries, so that the particle cannot leave without acquiring more energy than it has. An electron inside an atom experiences something like this. A particle inside a box, one of the simplest quantum systems physicists use to think with, experiences the purest version of it. The details of the trap do not matter yet. What matters is the act of confinement itself and what it immediately implies. Confining a particle means restricting where it can be. The position distribution, which in a free, unconfined particle can spread across an arbitrarily large region of space, is now bounded. The particle is somewhere inside the trap, not outside it. The range of possible positions has been compressed from effectively infinite to the physical size of the confining region. Make the trap smaller, and the position distribution compresses further. The particle is now somewhere inside an even smaller range. That compression is not a neutral act. It has a direct consequence that follows immediately from everything said in the previous two segments. A narrower position distribution means a wider momentum distribution, not probably wider, not approximately wider, necessarily wider by the same structural relationship that makes precise position and precise zero momentum mutually exclusive. Squeeze the position spread and the momentum spread pushes back in the opposite direction, expanding to compensate. This is already something. Before any calculation, before any equation, the act of placing a particle inside a trap has forced a conclusion. The particle's momentum is no longer free to settle wherever it likes. It has been given a minimum spread by the confinement itself, a spread that is larger the smaller the trap, and smaller the larger the trap, but never zero regardless of how the trap is configured. A confined particle carries a momentum distribution as a structural consequence of being confined. It did not choose this. Nothing pushed it into motion. The confinement alone was sufficient. What that mandatory momentum spread means for the particle's energy is where the argument tightens into something unavoidable. Hold a guitar string down against the fretboard. The moment your finger makes contact, the string's freedom of movement is reduced. It can no longer vibrate across its full length. The vibrating portion is now shorter, more confined, and the pitch it produces is higher. Tighten the confinement further, move your finger up the neck, and the pitch rises again. The relationship is direct and physical, and anyone who has held a guitar has felt it without necessarily thinking about what it means. Shorter string, higher frequency, less space, more energetic vibration. That relationship is not just an acoustic coincidence. It is a physical principle that runs all the way down to the quantum scale, and at that scale, it stops being about strings and starts being about something more fundamental. A particle confined to a smaller region does not just vibrate at a higher frequency the way a string does. Its momentum distribution widens, and a wider momentum distribution means something immediate and unavoidable about its energy. This is where the argument stops being abstract and becomes a one-way street. The position distribution has been compressed by the confinement. The momentum distribution has widened in response. That widened momentum distribution is not centered on zero. It cannot be, because a distribution centered on zero with significant width means the particle is equally likely to be moving in any direction at any speed, which is a real physical state, but it is not stillness. The average momentum can be zero, the spread cannot, and it is the spread, not the average, that determines the kinetic energy. Kinetic energy depends on momentum squared. Squaring removes the sign. A particle moving left and a particle moving right contribute equally to the kinetic energy regardless of the direction. So even if the positive and negative momenta in the distribution cancel each other out on average, their squares do not cancel. They add. A momentum distribution with any width at all, centered anywhere, produces a non-zero average of momentum squared, and therefore a non-zero kinetic energy. The confinement has not just spread the momentum, it has guaranteed that energy is present. Structural energy. Energy that was not put in from outside, but that arose from the geometry of the trap itself. No energy was added to the system. Nothing pushed the particle. Nothing heated it or struck it or transferred anything to it from outside. The only thing that happened was confinement. The particle was placed inside a bounded region, and the momentum spread followed as a structural consequence, the way a shadow follows an object when light falls on it. Not caused by anything dynamic, caused by the geometry of the situation alone. This is unfamiliar because at everyday scales, confinement and energy are not automatically linked in this way. Put a marble inside a box and the marble does not spontaneously acquire momentum because of the box. It sits where you place it. The box imposes a boundary, but the marble is not obligated to respond to that boundary with motion. Classical physics allows a confined object to be completely still. The confinement and the energy are independent facts about the system. At quantum scales, they are not independent. The position spread and the momentum spread are the same fact expressed in two different ways. Restricting one is identical to expanding the other. They are not two separate properties that happen to be correlated. They are two faces of a single underlying reality about what a quantum state is. And because kinetic energy is determined by momentum, and momentum spread is determined by position confinement, the energy of the system is determined by the geometry of its confinement. Tighter trap, higher mandatory energy. No exceptions, no workarounds, no configurations that escape the relationship. What this means in practice is that the question of how much energy a confined quantum particle must carry is not a question about the particle at all. It is a question about the trap. The particle is almost incidental. Given any confining potential, the minimum energy the particle can possess is already fixed by the size and shape of the confinement before the particle has done anything. Before it has interacted with anything, the energy floor is written into the geometry, and the particle has no choice but to sit above it. There is a tempting escape route that needs to be closed before moving forward. If the momentum distribution is spread across positive and negative values symmetrically, the average momentum is zero. A particle equally likely to be moving left as right has no net momentum in either direction, and if the average momentum is zero, perhaps the kinetic energy is also zero. Perhaps the spread cancels itself out, and stillness is recovered through the back door. It does not work that way. The confusion arises from treating average momentum and kinetic energy as the same thing, which they are not. Average momentum describes the net tendency of the particle to drift in a particular direction. Kinetic energy describes something different. It describes how much motion is present regardless of direction. A room full of people moving in random directions has zero net momentum as a group, but enormous kinetic energy because everyone is moving. The directionality cancels, the motion does not. Kinetic energy at the quantum scale is proportional to the average of momentum squared, not the average of momentum. Squaring momentum before averaging it removes the directional information entirely. A momentum of +3 and a momentum of -3 are different directions, but identical contributions to kinetic energy. When you square them both, you get 9 either way. Average them, and you get 9, not 0. The cancellation that worked for the average momentum does not survive the squaring. So, a momentum distribution that is perfectly symmetric around 0, which is exactly what a confined particle in a stable state tends to have, still produces a non-zero average of momentum squared. The wider the distribution, the larger that average becomes, and there is no configuration of a confined quantum particle in which the momentum distribution has 0 width. The confinement forbids it, which means the average of momentum squared is always positive, the kinetic energy is always positive, and the particle always carries energy it cannot shed, regardless of how the distribution is arranged or how symmetric it appears. The escape route is closed, the energy is there, it is real, and it is not going anywhere. Everything so far has been building toward a single conclusion that can now be stated without qualification. A quantum particle inside a confining potential always carries kinetic energy. Not usually, not under most conditions, always. The confinement produces a momentum spread. The momentum spread produces a non-zero average of momentum squared. The non-zero average of momentum squared is the kinetic energy. Each step in that chain is necessary, and none of them have exits. The word always deserves to sit for a moment. Physics is full of statements that are almost always true. True under normal conditions, true to a good approximation. This is not one of those. The chain from confinement to kinetic energy has no exceptions because each link in it is a structural relationship rather than a statistical tendency. It is not that confined particles tend to have momentum spread. It is that a quantum state with both precise position and zero momentum spread is not a state that exists in the mathematical structure of quantum mechanics. The framework does not contain it. Asking for a confined quantum particle with zero kinetic energy is like asking for a triangle with 4 sides. The request is grammatically coherent but physically empty. What this does to the classical picture is worth being clear about. The classical ground state, the configuration where a particle sits at the bottom of its potential well with zero momentum and zero kinetic energy, is not an idealization that quantum mechanics refines or corrects. It is a fiction that quantum mechanics eliminates. There is no quantum version of that state. The bottom of the potential well is not where the particle sits. It is a location the particle cannot occupy with any precision without its momentum becoming completely uncontrolled. And an uncontrolled momentum means energy. And energy means the particle is not at the bottom. The ground state exists. Every confined quantum system has one, but it is not the classical ground state dressed up in quantum language. It is something genuinely different, a state with real energy baked into it, a floor below which the system cannot descend no matter what is done to it. How high that floor sits, and why it sits exactly where it does, is where the argument goes next. There is one more escape route worth examining before the ground state energy floor becomes unavoidable. Kinetic energy is not the only energy a confined particle carries. It also carries potential energy, determined by where it sits within the confining potential. At the bottom of the well, the potential energy is at its minimum, typically defined as 0. Moving away from the bottom raises the potential energy. The total energy of the particle is the sum of both. So here is the attempt. If the particle cannot have 0 kinetic energy, perhaps it can position itself somewhere up the slope of the potential well, where the potential energy is negative relative to some reference point, and use that negative potential energy to cancel the positive kinetic energy. Total energy 0. Stillness recovered not through eliminating kinetic energy, but through offsetting it. The attempt fails, and the reason it fails is the same reason every other escape route has failed. Positioning the particle away from the bottom of the well means positioning it in a region of space with a specific location. A specific location means a tighter effective confinement, in the sense that the particle is now being held not just by the walls of the trap, but by the slope of the potential, pressing it back toward the bottom. That additional positional constraint tightens the position distribution further. A tighter position distribution means a wider momentum distribution. A wider momentum distribution means more kinetic energy. The attempt to reduce total energy by climbing the potential slope generates more kinetic energy than the potential energy gained, and the total energy rises rather than falls. The bottom of the well is where the potential energy is lowest, but it is also where the positional confinement is tightest, which is where the kinetic energy is highest. Every position away from the bottom trades lower kinetic energy for higher potential energy, but the trade never comes out even. There is a specific location where the sum of the two is minimized, and that location is not at the bottom, and the minimum sum is not 0. That minimum is the ground state energy, the floor, and it is above 0 by an amount the system has no mechanism to reduce further. The distinction between lowest permitted and lowest imaginable is not a subtle one, it is the entire point. The classical ground state, zero momentum, fixed position and zero energy, is imaginable. It can be described in words. It can be written as a set of numbers. It simply cannot exist as a physical state of a quantum system. The universe does not offer it. The ground state that quantum mechanics produces in its place is not an approximation of the classical one. It is a different kind of thing entirely, one whose energy is real, present, and irremovable. Irremovable is the word that carries the most weight here. Energy that is merely difficult to extract is still, in principle, available. The thermal energy in a cold object is hard to harvest usefully, but it is there, and given the right conditions it can be transferred elsewhere. The energy of the quantum ground state is not like this. It cannot be transferred because there is no lower state to transfer it into. The ground state is defined as the lowest permitted configuration. Moving energy out of it would require the system to occupy a state below the ground state, and no such state exists. The energy has nowhere to go. This makes it categorically different from every other form of energy encountered in ordinary experience. Chemical energy can be released through reactions. Thermal energy can be radiated away. Gravitational potential energy can be converted to motion. Every familiar form of energy is energy in transit, energy that is somewhere temporarily on its way to being somewhere else. Ground state energy is not in transit. It is not stored. It is not potential in the sense of waiting to be released. It is structural. It is part of what the system is, rather than something the system has. A hydrogen atom in its ground state is not holding energy the way a compressed spring holds energy. It is not waiting to release anything. The energy is woven into the configuration itself, inseparable from the fact of the atom's existence in that state. Cool the atom, slow its thermal motion, remove every external energy source, and the ground state energy remains. Not because cooling was insufficient, because cooling was never relevant to it. The ground state energy is not just non-zero, it has a precise value, and that value is not arbitrary. For the simplest quantum system that captures the essential physics, a particle in a harmonic potential, the kind of smooth bowl-shaped well that appears throughout physics whenever something is displaced slightly from equilibrium, the ground state energy works out to exactly 1/2 of the fundamental energy unit associated with that system. Not one full unit, not some complicated fraction, 1/2. That fraction is worth understanding because it is not a coincidence or an accident of calculation. It reflects something precise about the balance between position confinement and momentum spread at the ground state. The harmonic potential has a specific shape, a shape that tightens symmetrically as the particle moves away from the center in either direction. That symmetry produces a ground state wave function with a specific width, and that width represents the exact compromise between two competing pressures. Tighten the wave function, and the position is more constrained, but the momentum spread rises, and with it the kinetic energy. Loosen the wave function, and the kinetic energy drops, but the particle is now spending more time in regions of higher potential energy. The ground state sits at the precise point where the total energy, kinetic plus potential, is minimized, not zero, minimized. The half quantum that results from that minimization is called the 0-point energy of the oscillator. 0 point because it is the energy present at the 0 point of temperature, the energy that remains when everything that can be removed has been removed. It is the irreducible residue of the uncertainty principle applied to a confined system. Every harmonic oscillator in nature, every vibrating bond in a molecule, every mode of a vibrating solid, every oscillating field in the vacuum of space carries this half quantum at minimum. It cannot be cooled away. It cannot be extracted. It sits at the bottom of every oscillating system in existence as a permanent structural feature of what those systems are. There is a physical picture behind all of this that has been implied, but not yet made explicit. A quantum particle confined inside a potential well is not a point sitting somewhere inside the well with some probability of being at each location. It is a wave, not a wave in the sense of a water wave or a sound wave, not a wave in any medium, but a wave in the sense that its physical state has the mathematical structure of a wave, with peaks and troughs and a characteristic spatial frequency that encodes everything about its momentum and energy. Run a finger along a bathtub, and the water surface forms a wave that sloshes back and forth, reflecting off the walls and interfering with itself. The confined quantum particle does something analogous but more constrained. Its wave function must fit inside the well the way a vibration must fit inside a resonating cavity. The walls impose a condition. At the boundaries of the well, the wave function must go to zero, because the particle cannot exist outside the well at this level of approximation, and a wave that must be zero at both ends and non-zero in between has a minimum spatial frequency it must satisfy. It must complete at least a half cycle between the walls. It cannot be flatter than that and still meet the boundary conditions. That minimum spatial frequency is not an aesthetic requirement. It is directly connected to momentum. A wave with a short spatial wavelength corresponds to a particle with high momentum. A wave with a long spatial wavelength corresponds to a particle with low momentum. The longest wavelength that fits inside the well, the one that completes exactly half a cycle between the boundaries, corresponds to the lowest possible momentum consistent with the confinement. And that lowest possible momentum is not zero. A wave that completes half a cycle is not a flat line. It is curved. It has structure, and that structure is inseparable from energy. The flattest possible wave function inside the well is still a wave, and being a wave means carrying momentum, and carrying momentum means carrying energy. The ground state wave function is that flattest permitted wave, and its energy is the 0-point energy, present not despite the particle being in its lowest state, but precisely because the lowest state is a wave and waves cannot be still. Press on that point directly. What would a zero energy wave function actually look like? If the particle had no kinetic energy, no momentum, no motion of any kind, its wave function would have to reflect that. A particle with precisely zero momentum has a wave function that is completely flat, the same value everywhere. No peaks, no troughs, no spatial variation of any kind. A horizontal line extending uniformly across all space. That flat line fails immediately on two counts. The first is physical. A wave function that is the same value everywhere is not localized anywhere. It describes a particle that is equally likely to be found at any point in the universe, which is not a confined particle. It is the opposite of a confined particle. The moment confinement is imposed, the moment the well walls require the wave function to be zero at the boundaries, the flat line is ruled out. A function that is zero at 2 points, and the same non-zero value everywhere between them, is not flat. It is not even possible as a continuous function. The boundary conditions and the flatness requirement are mutually exclusive. The second failure is mathematical. The flattest function that satisfies the boundary conditions, zero at both walls, non-zero in between, is a smooth curve that rises from zero at one wall, reaches a maximum somewhere in the middle, and falls back to zero at the other wall. A half cycle. That curve is not flat, it bends, and bending has a precise mathematical meaning in quantum mechanics. The curvature of the wave function is directly proportional to the kinetic energy of the particle. A flat wave function has zero curvature and zero kinetic energy. Every other wave function has non-zero curvature and non-zero kinetic energy. The ground state wave function, that single smooth half-cycle between the walls, has the minimum curvature permitted by the boundary conditions, and that minimum curvature corresponds exactly to the zero-point energy. The curve itself is the energy. They are not two separate things. Curvature as energy is worth sitting with, because it is one of those correspondences that looks like a mathematical convenience, but is actually a physical statement about what energy means at quantum scales. In classical mechanics, energy is intuitive. A moving object has kinetic energy because it is moving. You can see the motion, measure the speed, calculate the energy from those measurements directly. The energy and the motion are visibly connected. In quantum mechanics, the particle does not have a trajectory. It does not move from one place to another in a way that can be watched or tracked. What it has is a wave function, and the wave function is what carries all the physical information about the particle's state. The momentum is not encoded in a velocity vector pointing somewhere. It is encoded in how rapidly the wave function oscillates in space. A wave function that oscillates quickly, that completes many cycles over a short distance, corresponds to high momentum. One that oscillates slowly, stretching its single half-cycle across a wide well, corresponds to low momentum. The spatial frequency of the wave is the momentum of the particle, translated into geometric language. Curvature is the rate at which the slope of a function changes. A rapidly oscillating wave changes slope quickly and has high curvature. A slowly oscillating wave changes slope gradually and has low curvature. So curvature and spatial frequency are directly linked, and spatial frequency and momentum are directly linked, and momentum and kinetic energy are directly linked. The chain is unbroken. Read the curvature of the wave function, and you have read the kinetic energy of the particle. They are the same information in different forms. This means that a wave function with zero curvature everywhere, a perfectly flat line, encodes zero kinetic energy, and a wave function that must curve to satisfy its boundary conditions encodes non-zero kinetic energy by the simple fact of its shape. The ground state wave function curves because it has to. The walls require it, and because it curves, the particle has energy, not energy that was put there. Energy that is there because the wave function is shaped the way it must be shaped, given the constraints it is under. Compress the well. Take the two walls and move them closer together. The wave function that was completing its half-cycle across a comfortable width now has to complete the same half-cycle across a shorter distance. The same curve compressed. A curve compressed into a smaller space is steeper. Steeper means higher curvature. Higher curvature means higher kinetic energy. The ground state energy of the smaller well is higher than the ground state energy of the larger well, and the relationship between them is precise and predictable. This is not an abstract result. It has consequences that show up in real physical systems in ways that are measurable and that matter. The electrons in a small atom are confined to a smaller region than the electrons in a large atom, and their zero-point energies reflect that. The protons and neutrons inside a nucleus are confined to a far smaller region than the electrons orbiting it, and their zero-point energies are correspondingly far higher, which is part of why nuclear reactions involve energies millions of times larger than chemical ones. The confinement scale sets the energy scale directly and without exception. Diamonds are harder than graphite despite both being made entirely of carbon. The difference comes down to how tightly the electrons are confined within the bonding structure of each material. In diamond, The bonds are shorter, the electrons more tightly confined, their zero-point energy is higher, and the energy required to deform the structure correspondingly larger. The hardness of diamond is not purely a classical phenomenon. It has a quantum mechanical flaw built into it, a resistance that comes from the fact that compressing the electron confinement further raises the zero-point energy, and the material pushes back. Take the compression to its logical limit. Make the well infinitely small, and the ground state energy rises without bound. There is no confinement tight enough to produce a zero-energy ground state, and no confinement loose enough to eliminate the ground state energy entirely. The flaw is always there, always positive, always scaling with the inverse of the confinement size. Confinement and energy are not just related, they are inseparable. Every form of energy encountered in ordinary life is energy that can, in principle, go somewhere else. The heat in a cup of coffee transfers to the air around it. The chemical energy in a battery drives a current and becomes light or motion. The gravitational potential energy of water behind a dam converts to electricity as the water falls. Energy moves. Energy transforms. Energy is always, in some sense, passing through a system on its way to being somewhere else. The cup of coffee cools because its thermal energy has somewhere to go. The battery dies because its chemical energy has been spent. The zero-point energy of a quantum system has nowhere to go. Not because the path is blocked or the mechanism is inefficient, because there is no lower state available to receive it. Extracting energy from a system means moving that system from a higher energy state to a lower one, with the difference appearing as heat or light or motion somewhere else. The ground state is the lowest state. Moving below it is not a slow process or a difficult process. It is not a process at all. The state below the ground state does not exist, and energy cannot flow into a state that does not exist. This places zero-point energy in a category with no classical equivalent. It is not potential energy waiting to be released. It is not thermal energy that could be removed by cooling. It is not kinetic energy that could be stilled by friction. All of those are energies that systems have temporarily, energies that are present because the system has not yet reached its lowest configuration. Zero-point energy is the energy of a system that has already reached its lowest configuration. It is what remains when everything removable has been removed, not a residue of incomplete cooling. The flaw itself, a system at absolute zero, the lowest temperature physically achievable, still carries its zero-point energy in full. Absolute zero does not mean zero energy. It means zero thermal energy, energy above the ground state. The ground state energy sits beneath absolute zero in the sense that no thermodynamic process touches it. Temperature is a measure of energy above the floor. Zero-point energy is the floor. The two are not in the same category, and cooling, however extreme, addresses only one of them. Everything established so far has concerned particles inside traps, electrons in atoms, particles in potential wells, confined systems with boundaries that impose curvature on wave functions and energy flaws on ground states. The natural assumption is that removing the trap removes the effect. Empty space, space with nothing in it, no particles, no boundaries, no confinement of any kind, should be exempt. A true vacuum should be the one place where zero-point energy does not apply, where the floor finally reaches zero and stillness is permitted. Empty space is not empty in the relevant sense. It is filled with fields. The electromagnetic field exists everywhere in space, not as a thing that travels through space, but as a property of space itself, a structure that pervades every point in the universe, and whose excitations are what we call photons and light and radio waves, and all the rest of the electromagnetic spectrum. The same is true of every other quantum field. They are all present everywhere, always, including in regions of space that contain no particles and no radiation. The vacuum is not the absence of fields, it is the ground state of fields. And fields, when analyzed quantum mechanically, decompose into modes. Each mode is a particular pattern of oscillation across space, characterized by a wavelength and a direction. The full field is the sum of all its modes simultaneously. Each individual mode behaves, mathematically and physically, exactly like a quantum harmonic oscillator. The same bowl-shaped potential, the same uncertainty relationship between position and momentum, translated into the language of fields as an uncertainty relationship between field amplitude and field rate of change, the same ground state, the same zero-point energy sitting at the floor of each mode, equal to 1/2 of the energy quantum associated with that mode's frequency. The vacuum is not one oscillator, it is every mode of every field simultaneously, each one sitting in its ground state, each one carrying its half quantum of zero-point energy. The total zero-point energy of the vacuum is the sum of contributions from every field mode, at every frequency, at every point in space. And that sum, it turns out, does not converge quietly. It grows without bound as higher and higher frequency modes are included, each one adding its contribution to the total. The vacuum is not calm. It is the simultaneous ground state of an infinite collection of oscillators, and the energy that implies is not small. The electromagnetic field stretched across all of space can be thought of as an enormous collection of independent oscillators, each one associated with a particular frequency and direction of oscillation. Low-frequency modes, long wavelength oscillating slowly, high-frequency modes, short wavelength oscillating rapidly. Every frequency that can exist does exist as a mode of the field, and in a universe with no upper limit on frequency, that means infinitely many modes. Each one sits in its ground state, each one carries half a quantum of energy at its particular frequency. Higher frequency modes carry more energy per mode because the energy quantum grows with frequency. The vacuum energy is the sum of all of these contributions across all modes at all frequencies. That sum does not converge. Add up half a quantum for every frequency from 0 to infinity, and the total grows without bound. This is not a sign that the physics is wrong. It is a sign that the calculation is incomplete, that at some very high frequency, the simple picture of a field as a collection of harmonic oscillators breaks down and new physics enters. Physicists handle this by introducing a cutoff, a maximum frequency beyond which the calculation is not trusted, and computing the vacuum energy up to that cutoff. The result depends on where the cutoff is placed, but for any reasonable cutoff, the vacuum energy density that emerges is enormous. How enormous depends on the cutoff chosen, but even conservative estimates produce a vacuum energy density many orders of magnitude larger than anything observed in the universe. The most natural cutoff, the scale at which quantum mechanics and gravity are both expected to be relevant simultaneously, produces a vacuum energy density roughly 120 orders of magnitude, larger than what cosmological observations suggest the vacuum energy actually is, 1 followed by 120 zeros. That discrepancy is not a rounding error or a minor theoretical tension. It is the largest known disagreement between a theoretical prediction and an experimental observation in the history of physics. The vacuum is full of energy that the calculation says should be there, and that the universe, as far as anyone can tell, is mostly not showing. But before reaching that tension, there are observations much closer to hand that confirm the vacuum energy is real, present, and physically consequential in ways that can be measured in a laboratory. Two metal plates placed parallel to each other in a vacuum, separated by a tiny gap, with nothing between them. No air, no fluid, no field sources of any kind introduced deliberately. Just two flat conducting surfaces facing each other across empty space. Classical physics predicts nothing happens. The plates are neutral, they carry no net charge, they exert no force on each other. Empty space between two neutral objects is just empty space. Nothing pulls, nothing pushes, nothing connects them. In 1948, the Dutch physicist Hendrik Casimir predicted that the plates would attract each other, not because of any classical force, but because of the structure of the vacuum between them. The prediction was precise and quantitative, a specific force depending on the area of the plates and the distance between them, derivable from first principles without any free parameters. The plates were eventually brought close enough together for the effect to be measurable, and the force was there, exactly as predicted. Two neutral objects in a vacuum attracting each other through nothing but the geometry of empty space. The mechanism is the vacuum mode structure described before. The vacuum between the plates contains field modes just as the open vacuum does, but with a constraint. The conducting surfaces impose boundary conditions on the electromagnetic field. The field must be zero at each plate, the same boundary condition that a wave function faces at the walls of a potential well. That constraint eliminates all field modes whose wavelengths do not fit an integer number of half-cycles in the gap between the plates. The vacuum between the plates contains fewer modes than the vacuum outside them. Fewer modes means less zero-point energy in that region. The energy density inside the gap is lower than the energy density outside it, and that difference in energy density produces a pressure. The plates are pushed together by the imbalance in vacuum energy on either side of them. The Casimir effect is not an indirect inference or a theoretical extrapolation. It is a direct mechanical consequence of vacuum zero-point energy, measurable with precision instruments, reproducible in laboratories, and in complete quantitative agreement with the predictions of quantum field theory. The vacuum pushes, not metaphorically, physically, with a measurable force. The Casimir effect demonstrates vacuum energy through geometry, through the way boundaries alter the mode structure of empty space and produce a measurable force. But the vacuum leaves its mark in other ways, more subtle and more intimate, visible not in the space between objects, but inside the objects themselves. Hydrogen is the simplest atom. One proton, one electron, a system clean enough that quantum mechanics can calculate its energy levels with extraordinary precision. In the 1940s, those calculations were good enough to predict the energy difference between two particular states of hydrogen, states that the theory said should be identical in energy, degenerate, sitting at exactly the same level with no separation between them. The prediction was clean and the reasoning behind it was sound. The two states should be the same. Willis Lamb measured them in 1947 and found they were not. The two states were separated by a small but precise energy gap, a shift that the existing theory gave no reason to expect. The measurement was careful and the result was clear. Something was pushing one of the states up relative to the other, something the calculation had not accounted for. That something was the vacuum. The electron in each of those two states occupies a different spatial distribution around the proton. One state keeps the electron closer to the proton on average, the other spreads it further out. The vacuum fluctuations, the ceaseless activity of every field mode in its ground state, interact with the electron differently depending on where the electron spends its time. An electron closer to the proton is more tightly confined, more sensitive to the vacuum fluctuations buffeting it, and those fluctuations shift its energy by a slightly different amount then they shift the energy of an electron in the more spread-out state. The two states, identical in the absence of vacuum fluctuations, are pulled apart by the vacuum's presence. The shift is small, precise, and in complete agreement with quantum electrodynamics once vacuum contributions are included. The hydrogen atom is not sitting in empty space. It is sitting in the ground state of all fields, and those fields are not passive. They interact with the atom continuously, leaving a measurable fingerprint on its energy levels that would not be there if the vacuum were truly empty. An atom in an excited state has more energy than it needs. Left alone in truly empty space, with no external fields, no passing photons, no disturbances of any kind, classical physics offers no mechanism for it to release that energy. The electron sits in its higher orbit and stays there. There is nothing to trigger a transition, nothing to push the electron down to a lower state. The excited atom should persist indefinitely in the absence of any external influence. It does not. Every excited atom eventually emits a photon and drops to a lower energy state, even in the most carefully isolated conditions experimentally achievable. The transition happens without any detectable external trigger. No photon arrives to stimulate it. No collision disturbs the atom. No external field nudges the electron. The decay simply occurs on a timescale characteristic of the transition, as if the atom made a decision to release its energy into the surrounding space. The vacuum made that decision. The field modes of the electromagnetic vacuum, each sitting in its ground state, each carrying its zero-point fluctuations, interact with the excited electron continuously. Those fluctuations are not large enough to be detected directly as incoming photons. They are the ground state activity of the field, present everywhere, affecting everything charged that exists within the field's reach. For an electron in an excited state, that interaction is enough. The vacuum fluctuations provide the perturbation that classical physics said was absent. They couple to the excited electron, stimulate the transition, and the atom emits a photon and drops to its lower state. Spontaneous emission is not spontaneous in the sense of uncaused. It is caused by the vacuum. Every photon ever emitted by an atom transitioning without external stimulation, every glow of every hot object, every flash of every excited gas, every laser that requires a population of excited atoms to eventually decay, all of it is driven at the fundamental level by the vacuum's refusal to be still. The ground state of the electromagnetic field is not a passive backdrop. It is an active participant in every radiative process in nature, present in every interaction, visible in every photon that was never asked for but came anyway. Two neutral atoms, far enough apart that their electron clouds do not overlap. No chemical bond between them, no ionic attraction, no permanent dipole moments pointing toward each other. Classical electrostatics says there is no force. The atoms are neutral. Their charge distributions are symmetric. At sufficient separation, there is nothing for electromagnetism to act on and nothing to produce an attraction. And yet neutral atoms attract each other across empty space. Not strongly, not at the distances where chemical bonds form, but measurably, persistently at distances where no classical force should be operating. This attraction is what allows noble gases, atoms with no chemical reactivity whatsoever, to condense into liquids at low enough temperatures. It is what makes gecko feet stick to smooth surfaces through millions of tiny hairs making contact with a wall. It is what holds together the layers of graphite that make a pencil mark on paper, a force with no classical explanation, operating between objects that classical electrostatics insists should not interact. The vacuum mediates it. Each neutral atom, despite having no permanent dipole moment, is subject to vacuum fluctuations that momentarily distort its electron cloud in a random direction. For an instant, the atom has a fluctuating dipole, a slight asymmetry in its charge distribution induced by the vacuum field. That fluctuating dipole generates a fluctuating electric field that propagates outward from the atom. A neighboring atom sits in that fluctuating field, and its own electron cloud is distorted in response, developing its own momentary dipole correlated with the first. Two correlated dipoles attract each other. The interaction is brief, random in direction, averaging to zero over time in terms of direction, but always attractive in terms of energy. The correlation is what produces the net effect. The vacuum fluctuation on one atom induces a response in the other, and the two fluctuations, linked through the field between them, pull the atoms together. At short range, this effect was understood before quantum field theory made the vacuum explicit. At long range, distance is large enough that the time taken for the field disturbance to travel between the atoms becomes significant. The correlation weakens, and the force falls off more steeply than the short-range version. Hendrik Casimir and Dirk Polder calculated this long-range correction in 1948. The same year Casimir published his plate calculation, and the retarded van der Waals force they derived has since been confirmed experimentally. The vacuum is not just pushing plates together and shifting hydrogen energy levels. It is the mechanism behind every weak attraction between neutral objects at any scale. 3 distinct measurements now confirm that vacuum energy is physically real. The Casimir force between plates, the Lamb shifts in hydrogen, the van der Waals attraction between neutral atoms. Each one is a different physical consequence of the same underlying fact, that the ground state of quantum fields is not inert, but active, not empty, but structured, not zero, but finite and measurable. Quantum field theory accounts for all 3 with precision. The vacuum energy is not a theoretical artifact. It is something the universe demonstrably contains, which makes what happens next genuinely difficult to absorb. General relativity, the theory that describes how energy and mass curve space-time and produce gravity, treats vacuum energy as a source of gravitational effect. Energy curves space-time regardless of what form that energy takes. If the vacuum has energy, the vacuum gravitates. A universe filled with vacuum energy would have that energy contributing to the overall curvature of space-time, affecting how the universe expands, determining whether the expansion accelerates or decelerates, leaving a measurable imprint on the large-scale structure of space itself. Cosmological observations constrain how large that contribution can be. The observed expansion history of the universe, the distribution of galaxies across cosmic scales, the geometry of space-time as measured through the cosmic microwave background, all of these set limits on how much vacuum energy the universe actually contains. The number they point to is small, not zero. There is evidence for a non-zero cosmological constant, a small positive vacuum energy driving the accelerating expansion of the universe, but small, extraordinarily small by the standards of what quantum field theory predicts. The theoretical prediction, summing zero-point contributions from field modes up to the scale where quantum gravity is expected to become relevant, produces a vacuum energy density roughly 120 orders of magnitude larger than the observed value. The calculation and the observation are not slightly inconsistent. They are separated by a factor larger than any other discrepancy in the history of physics. Something is almost perfectly cancelling the enormous vacuum energy that quantum mechanics says must be there, leaving only the tiny residue that cosmology observes, and nobody knows what that something is. The discrepancy is not a calculation error waiting to be found. Physicists have been looking for that error for decades. The calculation itself is straightforward, the same logic that correctly predicts the Casimir force and the Lamb shift, extended to include all field modes up to the scale where the theory is expected to break down. The individual pieces of the calculation are confirmed by experiment. The result they produce when combined is 120 orders of magnitude too large. Several proposals exist for how the discrepancy might be resolved. Supersymmetry, a theoretical framework that pairs every known particle with a partner particle of different spin, predicts that the zero-point contributions of particles and their superpartners cancel each other out, reducing the vacuum energy dramatically. But no superpartner has ever been detected, and the cancellation supersymmetry predicts is exact only if the symmetry is perfect, which it clearly is not at observable energies. Other proposals invoke additional fields, extra dimensions, or modifications to gravity at large scales. None have produced a calculation that matches the observed value from first principles. What makes the situation stranger is that the observed vacuum energy is not just small, it is small in a way that seems almost deliberate. A vacuum energy much larger than observed would have caused the universe to expand so rapidly after the Big Bang that no structures, no galaxies, no stars, no planets, no chemistry would have had time to form. A vacuum energy slightly negative would have caused the universe to collapse long before complexity could emerge. The observed value sits in the narrow range compatible with the existence of everything that exists. Whether that is a coincidence, a selection effect, or a clue pointing toward physics not yet understood, remains one of the deepest open questions in all of science. The descent that began with a pendulum coming to rest has ended somewhere considerably stranger. What looked like a simple question about energy at the bottom of things turned out to be a question about the structure of reality itself. The zero-point energy of a single confined particle is already a statement that the universe has a minimum below, which physical systems cannot descend. Extend that to every field mode at every frequency across all of space, and the statement becomes something larger. The vacuum is not the absence of everything, it is the ground state of everything. The baseline condition of the universe is not stillness and emptiness, but structured, energetic, irreducibly active. Every constraint in nature carries an energy cost. Every confinement raises a floor. Every boundary imposes a curvature, and every curvature encodes energy that cannot be removed, because removing it would require the system to exist in a state the universe does not offer. This is not a peculiarity of quantum mechanics. It is what quantum mechanics revealed about the nature of physical law. Laws are not just rules that systems obey. They are constraints that systems cannot escape, and constraints at the quantum level are never free. They always cost something. The cost is always energy, and that energy is always real. The vacuum energy problem sits at the boundary of everything currently understood. The same framework that predicts the Casimir force with extraordinary precision predicts a cosmological vacuum energy that is catastrophically wrong. Something is missing. The reconciliation of quantum field theory and gravity remains incomplete, and the vacuum energy is where that incompleteness is most visible and most consequential. Whatever resolves it will not merely fix a number. It will require a deeper understanding of what energy,